Divisibility in ultrafilters is a fundamental concept in set theory and topology, and this paper delves into the notion of divisibility relations on ultrafilters, denoted by specifically f, G if and only if every set in F that is upward closed for divisibility also belongs to G. The authors generalize the process of determining the basic divisors of an ultrafilter, which are obtained as equivalence classes of powers of prime ultrafilters. The paper describes the first omega levels of the quasiorder and provides a framework for determining the basic divisors of an ultrafilter. The authors utilize methods from nonstandard analysis to define the pattern of an ultrafilter, consisting of its basic divisors and their multiplicities. These patterns are shown to have a certain closure property in an appropriate topology. The authors rely on the Stonesetch compactification of the natural numbers, denoted by beta n, a fundamental concept in topology. They extend functions and binary operations from the natural numbers to beta n, particularly the extension of multiplication, to define a right topological semi-group structure on beta n. This builds upon previous work, including 11, which proposed various ways to extend the divisibility relation to beta n. The paper provides a more comprehensive and general framework for understanding divisibility in ultrafilters. The mathematical framework involves concepts from set theory, topology, and nonstandard analysis, employing precise mathematical notation. The authors demonstrate that every pattern with the closure property is realized by an ultrafilter, and isolate the family of sets belonging to every ultrafilter with a given pattern. The research paper explores the concept of a partial order on equivalence classes in the context of number theory and ultrafilter extensions. It introduces the definition of a relation, tilde-wide, which is a partial order obtained through an equivalence relation equals. This order is defined as f, tilde-wide, G if for every a element of F, a up-pointing arrow element of G, where a equals n element of n. There is a in a, n. An alternative condition for f, tilde-wide, G is also provided, stating that f intersection U subset equal G, where U equals a element of phosphorus mononitride, empty set, a equals a up-pointing arrow. The paper explains that tilde-wide can be thought of as a partial order on equivalence classes, f, tilde operator element of beta n, equals, and notes that n, tilde-wide, G means G equals nf for some f element of beta n. But this is not true for n element of beta n in general. Various notations and definitions are recalled and introduced, including the set of primes P, the set of prime powers P exp, and different operations on sets such as n, a1 a2, n, a down pointing arrow, and v. The family of all convex subsets of n, denoted as C, is defined, with U subset equal C, and F intersection C determining the equals tilde operator class of an ultrafilter F. The paper highlights that various aspects of beta n equals tilde-wide have been considered in previous papers, including facts on the first omega levels of this order. Ultrafilters, a concept in nonstandard arithmetic, are central to the discussion on their properties and relationships. The levels lane of ultrafilters consist of ultrafilters that concentrate on the set lane equals P1 P2, Pn, P1, P2, Pn element of P. These prime ultrafilters in P generate the square P2 of P element of P, which is different from Pp, belonging to the family of ultrafilters, twice divisible, by P and containing not the sets A2 but A2, for a element of P upwards harpoon barb rightwards P. Basic ultrafilters, being powers of primes Pk, for P element of P and K element of N, fragment all elements of L. Each ultrafilter in lane has exactly N, not necessarily distinct, basic divisors, with each Pk counted K many times. A pattern, alpha F, mapping each basic ultrafilter to its multiplicity within F, corresponds to every F element of L. This pattern determines the basic divisors of F through a family F alpha F subset equal F intersection U. A corollary of theorem 3.6 from 13 serves as a counterexample, stating that there is P element of P, sup that, for every n greater than 1, there are at least two ultrafilters F, G element of LAN distinct from Pn having Pa their only basic divisor. Unlike in L, the relation tilde operator is not well-founded in general, and ultrafilters cannot be organized in levels. To fragment each ultrafilter into basic ones, the paper utilizes methods of nonstandard arithmetic, introduced into the context of ultrafilter divisibility, and 14. Nonstandard extensions are introduced via superstructures, where V0, x, equals x, Vn plus 1, x, equals Vn, x, union P, Vn, x, for n element of omega, and V, x, equals n area union n less than omega Vn, x. The nonstandard extension is a pair, V, y, asterisk operator, where V, y, is a superstructure with the set of atoms Y superset equal x and asterisk operator. V, x, right pointing arrow V, y, is a function such that asterisk operator x equals y and satisfying the transfer principle. This principle states that for every bounded formula phi, x1, xn, and every a1, a2, an element of V, x, V, x, equals phi, a1, a2, and, if and only if V, y, equals phi, asterisk operator a1, asterisk operator a2, asterisk operator n. The concept of bounded first-order formulas is introduced, where all quantifiers are bounded, taking the form, for all x in y, or, there is x in y. In these formulas, free variables x1, x2, xn can take on any values a1, a2, an element of V, x, which are replaced with asterisk operator I element of V, y, on the right-hand side. Atomic subformulas take the form a, x1, xk, for some carry relation a element of V, x, which is also replaced with asterisk operator a. The star counterpart of phi, x1, x2, xn, denoted by asterisk operator phi, x1, x2, xn, is obtained by adding stars to all values of free variables except those explicitly stated. Several examples illustrate this concept, including the equivalence of asterisk operator n, and asterisk operator a, n, asterisk operator a, n, and asterisk operator a, n, and asterisk operator a up pointing arrow, and asterisk operator a up pointing arrow. Furthermore, if dom f equals a subset equal n, then dom asterisk operator f equals asterisk operator a. A connection is established between nonstandard and ultrafilter extensions of n, where for every x element of asterisk operator n, Tp, x, n, is an ultrafilter, and x is called a generator of that ultrafilter. This is extended to functions f, n right pointing arrow n, where Tp, asterisk operator f, x, n, equals tilde operator Tp, x, n, for every x element of asterisk operator n. The distinction between prime nonstandard numbers p and their respective ultrafilters, as well as their powers pk corresponding to basic ultrafilters pk, is exemplified. The concept of internal sets and atoms is introduced, where sets belonging to some asterisk operator a for a element of V, x, are called internal. The internal definition principle states that sets defined from internal sets are also internal. Finally, the notion of hyperfinite sets S, which are sets in asterisk operator, n, less than, is introduced, where n, less than is the family of finite subsets of n. In the context of mathematical logic and model theory, nonstandard extensions of Peano arithmetic are models that contain nonstandard numbers, which are either greater than any standard natural number or less than any standard natural number. The internal cardinality of a set S in a nonstandard extension is the unique T element of asterisk operator n for which an internal bijection f 1, 2, T right pointing arrow S exists. This research focuses on C+ saturated nonstandard extensions, which possess desirable properties, such as ensuring that every initial segment of the form x element of n, x is less than or equal to z, for z element of asterisk operator n, n has the same cardinality, denoted by infinity. This condition can be achieved through Henson's C+ isomorphism property, without requiring additional set theoretic assumptions. The monad micro, f, of an ultrafilter f element of beta n is defined as the set of all x element of asterisk operator n such that Tp, x, n, equals F. Key proposition establishes the equivalence of four conditions for two ultrafilters F and G in beta n, involving the relationship between the divisibility relations and asterisk operator, as well as the existence of certain elements in the monads of F and G. The concept of assets, subsets of P, is introduced, along with a function ha. Pa right-pointing arrow n that maps each P element of Pa to the minimum n element of n such that Pn element of A. The relationship between ha, P, and the divisibility relations, and asterisk operator, is explored, showing that for P element of asterisk operator P, asterisk operator Pa, no power of Pn is asterisk operator A. This implies that F needs to contain all element of U for which asterisk operator ha, P, is less than or equal to X in order for Tp, Px, n, tilde wide, F to hold. Finally, the concept of the limit ultrafilter G equals limi right-pointing arrow WFI is discussed, defined as the ultrafilter on I such that a element of G if and only if I element of I, a element of phi, element of W. A lemma from 15 is referenced, stating that the limit ultrafilter G can be constructed using a set of ultrafilters, phi, I element of I, and an ultrafilter W on I. In nonstandard analysis, ultrafilters play a crucial role. Proposition 1.4 establishes that every chain of ultrafilters has a least upper bound and a greatest lower bound, which can be obtained as the limit of the chain. Furthermore, the intersection and union of the ultrafilters in the chain can be characterized in terms of the least upper bound and greatest lower bound. Proposition 1.5 focuses on internal sequences of ultrafilters in nonstandard extensions. It shows that for every internal sequence, there exists a unique element in the nonstandard extension that satisfies certain divisibility properties. Conversely, every element in the nonstandard extension can be represented as a product of ultrafilters satisfying certain conditions. The product of two ultrafilters F and G is defined as a tau minimal ultrafilter divisible by both F and G. However, it is noted that there may be multiple ultrafilters satisfying this property, and the product of two ultrafilters may not always belong to the product of the ultrafilters. Proposition 1.6 provides an equivalent condition for a pair of ultrafilters to be a tensor pair, which is a necessary condition for the product of the ultrafilters to belong to the product of the ultrafilters. Lemma 1.7, a version of Theorem 11.5.12 from 1, states that if X and Y are ultrafilters such that the pair X, Y belongs to the ultrafilter H, then for every ultrafilter X in the ultrafilter F, there exists an ultrafilter Y in the ultrafilter G such that X, Y belongs to H. This lemma has implications for the existence of tensor pairs of ultrafilters. Overall, this section develops the theory of ultrafilters and nonstandard analysis, providing several key results that will be used in later sections of the paper. These results lay the foundation for further exploration of ultrafilters and their applications in nonstandard analysis. In the realm of nonstandard models, ultrafilters exhibit intriguing properties and behaviors. This section delves into the intricacies of these ultrafilters, particularly focusing on the divisibility order. A key proposition is introduced, stating that if P is a prime number, all ultrafilters Tp, Px, n, for X and n are equals equivalent. However, this proposition does not hold true for P and P, as demonstrated through an example. The paper then presents a definition for the relation approximately equals P on micro, P, times n, which is defined as P, x, approximately equals P, q, y, if and only if Tp, Px, n, equals Tp, q, y, n. This relation forms an equivalence relation, and the set of its equivalence classes is denoted as EP equals P, x, approximately equals P, x, element of micro, P, times n. The vertical sections are defined as up equals X, P, x, element of U, where U is an element of EP. These sections are not independent of the choice of P, as shown in example 2.2b. This example also demonstrates that any two prime nonstandard numbers have powers Px and Qx such that Tp, Px, n, approximately equals Tp, Qx, n. indicating that any two prime non-standard numbers have powers with equivalent ultrafilters. This section provides a comprehensive exploration of ultrafilters in non-standard models, examining their properties and behaviors under different conditions. It introduces a key proposition about the equivalence of ultrafilters for prime numbers, provides a counterexample for non-prime numbers, and defines a relation approximately equals p to classify these ultrafilters further. The concept of vertical sections is also introduced, highlighting the interdependence of these sections on the choice of p. The concept of basic families of ultrafilters, denoted as PU, is introduced, where each PU is a set of ultrafilters of the form Tp, Px, n, for some p element of P and U element of Ep. The measure of PU, denoted as micro, PU, is defined as the union of the measures of all f in PU. The set of all basic classes is denoted as B. The authors consider the tilde operator classes PU as powers of P. Properties of basic ultrafilters are established in Lemma 2.5, including that all elements of micro, PU, are of the form Px, and that for every P element of micro, P, the setup is non-empty and convex. Definition 2.6 introduces a relation precedes P on EP, where U precedes PV if and only if U, E equals V and there exist P element of micro, P, and X, Y element of asterisk operator N such that P, X, element of U, P, Y, element of V, and X less than Y. Properties of this relation are discussed in Lemma 2.7, including that it is a strict linear order, and every increasing or decreasing sequence has a supremum or infimum, respectively. The page also presents proposition 1.3, which implies that if U precedes PV, then for all P in micro, P, and all X, Y element of asterisk operator N such that P, X, element of U and P, Y, element of V, X less than Y holds. The proof of Lemma 2.7 is presented in three parts. Part A is straightforward, while Part B assumes that the given sequence is well-ordered without loss of generality. It is demonstrated that the sequence of ultrafilters has a least upper bound G, and using proposition 1.4, it is proven that the cofinality of asterisk operator n is at least C+, implying the existence of an upper bound Z for x xi less than gamma. Then, using proposition 1.3, it is found that Y is less than or equal to Z such that Py element of micro G, making P, Y, approximately equals P the supremum of the given sequence. Part C directly applies theorem 4.6 from 15. Both cases from Lemma 2.5, C, are possible, with the first case occurring by example 2.2, A, and the second case being a union of galaxies. It is also shown that each EP has the greatest element Umax, denoted as Pmax, and for P element of P, P omega equals PU, where U equals sup omega in EP. Example 2.8 provides two results. Firstly, if Px is a tensor pair, then Px belongs to micro Pmax. Secondly, if x, P, is a tensor pair, then Px belongs to micro P omega. These results are proven using proposition 1.6 and the properties of tensor pairs. The notation is extended to include PU intersection U equals a element of U, a element of PU, and PU intersection C equals a element of C, a element of PU. The U topology on B is defined as the topology generated by base sets A for a element of U, and the closure of S subset equal B in this topology is denoted as CLUS. Finally, Lemma 2.9 states that the sets A for H, a right-pointing arrow n such that a subset equal P form a base of the U topology on B. In the realm of set theory, a pivotal concept is the relationship between sets and their properties under various topological and algebraic structures. This paper delves into this topic by first proving that for every set B in a universe U, there exists a set A such that A element of Q if and only if B element of Q. This is achieved through the definition of H equals HB as per equation 2. The proof then progresses to demonstrate that for any Q in B, B intersection PEXP element of Q so AHB equals B intersection PEXP, up pointing arrow element of Q. This establishes one of the desired implications. The significance of ultrafilters is also explored, highlighting their role in expanding the set of basic divisors. The paper further investigates patterns in the behavior of basic divisors, particularly in the context of infinite multiplicity. A new concept, d, u, v, x, is introduced, which involves the cardinality of sets based on prime divisors. A subsequent lemma demonstrates the existence of infinite subsets within d, u, v, x, leading to the conclusion that the cardinality of such sets can be infinite. This technical discussion is crucial for understanding the properties of sets and their relationships under various mathematical structures. In nonstandard models of Peano arithmetic, the concept of exact divisors plays a crucial role. A key set, denoted F, consists of pairs M, K, where a one-to-one function f maps 1, 2, k to a intersection PEXP, with a being an element of the intersection of three sets Q, PV, and C, the family of all convex sets. The main result, Theorem 3.3, establishes that for any x in the nonstandard model, the number of exact divisors from a given set is either finite or infinite. This theorem yields two significant corollaries. Firstly, the number of exact divisors from any subset of PEXP is either finite or infinite, and secondly, every element X has either a finite or infinite number of exact divisors from a given subset of PEXP. Furthermore, the paper introduces a set of comprising functions alpha, b right pointing arrow n infinity, referred to as patterns, which satisfy a specific condition involving summation over prime numbers. When P is a singleton, it is identified with pk and written as alpha pk, treating pk as a subset of B. The research aims to explore the properties of nonstandard models of Peano arithmetic, particularly in terms of exact divisors and their relationship with subsets of natural numbers. The findings contribute to a deeper understanding of these models and their potential applications in various areas of mathematics and computer science. U-closed patterns, denoted by ACL, are introduced to represent the quantities of each basic divisor of a given ultrafilter. A pattern alpha in A is considered U-closed if, for every A in Q intersection U, the condition n airy summation W element of Q alpha, QW, is greater than or equal to n holds whenever n airy summation PV element of A alpha, PV, is greater than or equal to n. Two sequences A and B in n infinity are said to dominate each other if, for every L in L, n airy summation M is greater than or equal to La M is greater than or equal to n airy summation M is greater than or equal to LBM. For alpha, beta in A, alpha precedes beta, alpha beta. If beta, S sequence dominates alpha, S sequence for every P and P if alpha beta and beta alpha, then alpha approximately equals beta. A key lemma is presented, stating that for U-closed patterns and P, three conditions are equivalent. I, beta, S sequence dominates alpha, S sequence. E, there exists a one-to-one function GP mapping union U element of EP, U, times alpha, P, to union V element of EP, V, times beta, PV, such that V superset equal P whenever GP, U, I, equals, V, J, and, E, there exists a function FP mapping union U element of EP, U, times alpha, P, to EP such that FP, U, I, superset equal P for every, U, I, in union U element of EP, U, times alpha, P, and, FP caret, 1, V, is less than or equal to beta, PV, for every V in EP. These conditions provide a framework for comparing and relating U-closed patterns, enabling the analysis of their properties and behaviors. The research paper presents two key results. Firstly, it proves the equivalence of conditions I, E, and E in a previous theorem. This is achieved by dividing the proof into two cases. In case 1, it assumes beta restricted to P dominates alpha restricted to P, and shows that a function g can be defined to satisfy condition E. Case 2 considers the situation where there exists a maximal element M in EP such that the sum of beta over P is infinite, and demonstrates that a function g can be defined to satisfy condition E, using a recursive construction. The implication from condition E to condition E is straightforward, and the implication from condition E to condition I is shown by constructing a function fp that satisfies condition I. Secondly, it presents theorem 3.10, which states that for any x in asterisk operator n, the pattern alpha x is U-closed. The proof involves showing that the family F of sets BA has the finite intersection property, achieved by demonstrating that each set BA is non-empty. By C plus saturation, it follows that alpha x is U-closed. Definition 3.9 is also introduced, defining alpha x, poo, as the cardinality of the set D, U, U, x for each basic poo in B. This definition is used in the proof of theorem 3.10. This refinement aims to condense the technical details of the research paper into a concise and accurate voiceover narration. It begins with a lemma that states if x asterisk operator, y, then alpha x precedes alpha y, explaining how this is proved through a function witnessing the domination of alpha x by alpha y. The theorem that follows asserts for any f element of beta n and two elements x, y element of micro, f, alpha x equals alpha y, which is proved by showing that if y element of asterisk operator xa, then x element of asterisk operator xa. The corollary states that if f tilde wide g, then alpha f precedes alpha g, and if f equals tilde operator g, then alpha f approximately equals alpha g, highlighting the importance of the pattern concept in the context of ultrafilters and their equivalence classes. The example illustrates scenarios involving the pattern alpha f determining basic ultrafilters and their multiplicity, emphasizing the significance of the equals tilde operator equivalence class. This refined version maintains technical accuracy and depth, ensuring a smooth flow for the voiceover narration. The concept of alpha sets is crucial in the context of the research, defined as finite products of A, P, U sets, where the number of A, P, U sets in the product is bounded by a finite number. Alternatively, alpha sets are also defined as finite products of alpha, I, pi sets, with I element of pi, and pi, E, adio, / equals pj, and I intersection aj equals empty set for I, E, adio, / equals j. The intersection of U with the filter generated by alpha sets is denoted by f alpha. An example of a finite pattern alpha is demonstrated, showing how f alpha is generated by sets of the form a 2-up pointing arrow for element of P. The significance of finite patterns is highlighted, building upon previous work in 13. The filter f alpha generated by a pattern alpha in a CL exhibits distinct properties, which are explored in detail. The authors present several results characterizing the generation of f alpha for various pattern types, including those with a single pair, finite sets, infinite sets, and countable sets. Additionally, they investigate the relationships between f alpha and other filters, such as f beta, in the context of comparing patterns alpha and beta in a CL. For a single pair pattern, P1, with P element of P, theorem 4.1 shows that f alpha is generated by the sets a up pointing arrow for all element of P upwards harpoon barb rightwards P. This fundamental result is followed by a series of theorems describing the generation of f alpha for diverse patterns, including finite sets, infinite sets, and countable sets. Notably, theorem 4.3 establishes that for every f element of beta n, f alpha f subset equal f intersection U, implying that the filter f alpha generated by a pattern alpha is a subset of the intersection of the filter f and the set U. This finding is crucial for understanding the relationships between f alpha and other filters. Theorem 4.4 reveals a significant equivalence between two conditions: I, alpha precedes beta, and E, f alpha subset equal f beta. This equivalence highlights the intrinsic connection between the ordering of patterns in a CL and the inclusion relationships between their corresponding filters. These results collectively provide a comprehensive understanding of the properties and relationships of filters generated by patterns in ACL. The relationship between alpha sets and beta sets is further explored, focusing on their connection to the factorization of a set C specifically. It is demonstrated that if C is an beta A P set, then for every V element of EP, there are at most n airy summation W is defined as PV beta, PW, A. P is defined as V sets in the factorization of C. The proof of the opposite direction involves assuming the opposite and deriving a contradiction. This section also includes examples that highlight the necessity of the U-closedness condition in the theorem. Additionally, Lemma 4.6 and Theorem 4.7 are presented, which provide insights into the properties of tensor pairs and the relationships between ultrafilters. The construction of an ultrafilter G with a given U-closed pattern beta involves a step-by-step process starting from an initial pattern F. This process involves refining F iteratively based on the successor and limit ordinal cases. The authors also provide an example illustrating that not all U-closed patterns can be constructed in this manner. Additionally, they present a corollary stating that for every U-closed pattern beta, there exists an ultrafilter G such that alpha G approximately equals beta. A crucial aspect of beta being a U-closed pattern that is not finite lies in the possibility of choosing different ultrafilters at limit stages. This leads to the conclusion that for a specific beta, there can only be one ultrafilter F that satisfies certain conditions, a finding essential for Theorem 4.7 and Corollary 4.9. Assuming all sets of the form 1, 2, Z, for Z element of asterisk operator n have the same cardinality greatly simplifies working with patterns. This assumption enables the proofs of several results, including Theorem 3.3 and Lemma 3.8. The significance of Theorem 3.12 is also highlighted, as it ensures that properties learned about a pattern from a specific element are indeed properties of the pattern itself. The discussion concludes by posing several open questions, including the possibility of describing the order of EP with respect to P and the improvement of Theorem 4.7. Recent findings have shed light on these questions, hinting at further research in the area of ultrafilters and their properties. The elimination of an additional assumption is acknowledged, and gratitude is expressed for the referee's comments. Funding support is recognized from the Science Fund of the Republic of Serbia and the Ministry of Science, Technological Development, and Innovation. The author also acknowledges the significance of the feedback received.